So, hello everyone. Welcome to our third session of the Spring 2024 program for the Virtual Inter-University Symposium on Infrastructure Management. Today, Babatunde, Atolagbe, and Dadi Bhargavi will be presenting their work. Each presentation should be about 20 minutes long, after which we will take questions from the audience. You're welcome to speak your questions or send them using the chat. And I would like to point out that this meeting is being recorded and will be made available shortly after. And so thank you all for attending. And to start, I'm going to introduce Babatunde. So Babatunde Atolagbe is a PhD student in the Department of Civil and Environmental Engineering at the University of Delaware. His dissertation focuses on using machine learning to identify the appropriate decision support tools for asset management to different problem contexts. He completed a bachelor's degree from the University of Ilorin in Nigeria and a master's degree from University of Tennessee, Chattanooga, both in civil engineering. So without further ado, Babatunde, please take it away.
Thank you very much. Good day to everyone. My name is Babatunde, and today I'll be presenting my part of my research titled an exploratory framework for enhancing the explainability of network-based decision support tools for transportation asset management. So as we all know, that having effective strategies for infrastructure management is very important for the sustainability of our infrastructure. But we know that asset managers are often met with several challenges, like the fact that the infrastructure constantly ages, the fact that the traffic continues to grow, and the fact that there are usually multiple asset classes to make decisions from. And most importantly, because of limited funding. So we have to make some decisions, and we need to have like rigorous decision framework to make these decisions. And to do that, we need to use decision support tools. So decision support tools are a set of, for infrastructure asset management, a set of predefined rules or analytical models that uses some variables to make decisions about our infrastructure. And here is a figure that classifies decision support tools for infrastructure asset management. We have the simple tools, which are often in the form of decision trees that are found in pavement management systems, such that when the asset reaches certain threshold, so it triggers certain treatment actions. And then we have the complex tools, which are often based on optimization techniques, which can be a multi-objective or bi-level optimization and so on and so forth. And then we have the software tools, which are usually in the form of off-the-shelf tools that are readily available or accessible to the asset managers. So the distinction between simple rules and the complex rule is that because of the simplicity of the simple or the rule-based tools, they are simple to use, and as such, the modeling framework and the outcomes are very clear to understand, and they usually require lesser, analytical or computational resources to use them, unlike complex tools where the reverse is the case. But regardless of whether or not you're using it, we are using the simple or complex tools. The decision support tool is expected to meet these requirements, which include maximizing lifecycle performance, minimizing agency cost, and they should properly reflect the transportation network for which they are designed for. And they should also consider all variables that are important for the decisions, and they should eliminate bias in the models. Yeah, the unfortunate thing is that in the process of trying to capture all these requirements, we often get into a black box syndrome where you have a lot of variables in the model with limited understanding of the interrelationship between them. So in my experience with using black box models and also with support from literature, we find that black box models lack adequate understanding in terms of the variables, some uncertainties in them. And then usually the frameworks are usually complex for the users Mostly it's the person that designed them that really understands what to do with the framework. And there's also the problem of scalability, because usually these frameworks, when they are implemented on toy concepts, toy networks and so on and so forth. So when it's time to actually scale up to real networks or real instances, then it becomes a problem. And this often leads to lack of trust in this model from the point of view of the agencies that are going to use this model, the models. So this is an example of a complex IAM model. We have a model that is adapted from these researchers. Um, and the model is based on a bi-level optimization where you assess the states of the segments in a transportation network, and then certain actions are made on each of the segments. And the segments, because of the actions that are made, there's going to be some user cost and the disruption to the network, which can also be quantified in form of disruption cost. And the upper level is going to select the actions, and the lower level is going to assess the impact of the actions on the network. And because this is going to trigger a new state, it's going to repeatedly, the process is going to be repeated, like over the planning horizon, so that we can for the life cycle, to estimate the life cycle, total life cycle cost. So that's going to be repeated over the planning horizon. And we can see here that this model has some inputs like the network properties. We need to know the network structure, and then we have the traffic assignment properties, like what's the origin destination demand on the network. And then we have some model parameters, which could include something like the deterioration rates and the discount factor, and so on and so forth. And this model would have is designed to generate these outcomes: maintenance costs, the user cost, disruption costs, which are life cycle cost components. And we see here that there are so many variables here. So, and a lot is happening within the model. So this is a typical black box model where, as a user, you may not really understand what is going on in that. So what I'm doing in my research and this presentation, what I'll be doing is we're looking at how we can better understand the variables in the model. And the question we are answering is to know what variables or parameters are really important. Because when we know that, then we can set some of those parameters to some predefined values, and then that could potentially help us eliminate the process and the framework that is supposed to capture for the uncertainties in these variables. And yeah, sensitivity analysis is a technique that can be used to do that. It's not a new thing, but currently the current trend in IAM, infrastructure asset management, is local methods where you vary you vary a variable and you keep other variables constant, and you assess the outcomes so that you can compare, you can determine the influence of this changing variable on the outcome. And we have the global methods, which is what I'm proposing in this research, and I'm going to get there with an illustration in the coming slides. The second thing, question we are trying to address is, can we come up with a kind of generalizable pattern between the inputs and the outputs from the models? Like the inputs would be the scenarios, or like decision scenarios that we are faced with, want to make a decision under that scenarios. What is the outcome that we can expect for that scenario? And this would be useful because then we can know, okay, when you have multiple models to make decisions with, and you have some fidelity issues with one or more of them, we can then say that, okay, because we've done something like this, we can say that under certain instances, it is better to use this model, even though it lacks clarity, but because we've been able to establish that it is the best for that scenario. And I'm going to talk more about that in the coming slide as well. This is just a typical illustration of local sensitivity analysis, which is what I said is being done currently. We see here, this is going to offer us limited information because it only relates the cost, the outcome of the model to the variables individually. We do not see the additive, the relationship between the variables here. But what I'm proposing here, and without going into the details of the experiments and things like that, is a variance-based sensitivity analysis technique where you can see what the additive the interactions between the variables are on the decision outcomes. And we see here as an illustration here, when you look at the first order indices for this the simulation, we see here that it does look as if the iteration rate is not really important in the model. But then when you look at the global, all the total indices, we see here that deterioration rate is indeed important. So this is why we are proposing that in infrastructure asset management, we should begin to kind of, use variance-based method or, global sensitivity analysis technique to explore the sensitivities of our model outcomes to the input variables. Now, the other question, generalizing the model. This is a slide. I'm going to come back to this slide briefly, but why are we doing that? Let's look at a case study, some case study models. We have a model here where you have a predefined policy that tells you when certain actions should be done on certain segment, on the segments of the network. And when the actions are done, we're going to have to assess the agency cost due to the cost of maintaining those segments. And those actions, of course, they're going to induce some user cost. So we're going to capture that user cost. And because of the actions that we are carrying out on the network, there's going to be some disruption to that, maybe by virtue of closing segments partially or fully. So we need to assess that disruption cost as well. Now, this is a model. This is a simple model, but this model can become complex by, rather than focusing on one policy, to explore all feasible policies. And that's going to take significant time to do that, to explore all the policies and ultimately picking the policy that optimizes the life cycle cost. And the other model here is something similar to the first one, but the difference is that the second one is not assessing the disruption and the user cost components of the disruption cost, rather. That's a mistake there. The disruption cost. And how we're going to look at that is that when you look at a case study network like this, we have a network to demonstrate what's the application of this model. This network can either be heavily congested, it can be less congested, and it can be moderately congested. So we can say that if a network is heavily congested, then it may be important to use it becomes clear that we should use a complex model to really capture the disruption and all of the components of the cost in the model. But then when the network is not heavily congested, it means that there's going to be a lot of redundancies and the impact of the disruption on the network will be minimal. Then we can say that we can use a model that does not really reflect the disruption cost. But then the gray area would be between, the heavily congested and the less congested. So we need to kind of know under what scenario should we use certain model within that gray area. And that is why we are proposing a kind of framework like this to further explore the models so that we can understand the scenarios better to use them. So this is the framework. Basically, we generate the decision scenarios, which is, okay, what is the network structures and vary the parameters. And when we do that, we're going to characterize the scenarios by grouping them based on the similarities between the scenarios. So this is what is going to help us understand, okay, when is the scenario really complex and less complex and so on and so forth. And when we do that, the next thing is to really label the scenarios as shown here. This is kind of an illustrative process. So we're just saying that, okay, maybe what we can do is when we run the models, let's say we have 2 models or 3 models, we run the models on the different scenarios and we assess the total maybe life cycle cost. And then we can say that when the cost is within certain threshold, then we should use this model. When the cost exceeds certain threshold, then we can use a certain model. And that way we can label the model. And so the ultimate thing is that when we do that, we want to be able to predict that, okay, when we have a new scenario that we've not seen before, a new decision scenario, what model should we use? So this is why we're developing a kind of a classification model that would then take this label data sets and determine the right model to use for that scenario. So this is just a kind of brief background on network analysis. I believe most of us may be familiar with network analysis. We represent transportation network as form of graphs, which can be directed and undirected. And these are some properties that are assessed on the network analysis. I won't go into the details of those. And then we can have we have here the classification of these properties as either the local measures, which are only assessing the properties of the network at the node or at the edge level. And we also have the global measures, which provide some kind of numerical indicators for the whole network. And this is what we're using here because we have a lot of networks that we want to use to create scenarios. So assessing the global measures is of importance in this case rather than the local measures. So we have this here. And here is some definitions of the global or the network level measures. So the other thing that I want to quickly talk about here is the synthetic and the toy network, which is often the case when we implement the models for research purpose or for publication purpose. So typically because of lack of data, sometimes we have synthetic networks which are generated using some mathematical models to mimic real life situations, but they are not real life situations. And we have the toy networks which are very simple, like the one I showed previously, just to illustrate the application of the model that is being proposed. And they are very limited in their use because they do not really reflect the reality. So everything I've said, I just want to illustrate the process of generalizing the model. So I want to illustrate. I want to mention I do not really have real data here, but this is just an illustrative. I just generated some random data to illustrate the process of what I'm presenting here. So we have two models, like the black box and the simple model. And we want to determine that, okay, yeah, we know that the black box model is difficult to use. It takes a lot of time, usually significantly greater than the time required for the simple model. But under what scenario should we use? Would it be important, or can we say comfortably that, yes, we should use the complex model, or maybe just simply using the simple model? So the first thing I'm doing here is to kind of generate some synthetic, network or toy network here, and I generated 80 networks, as we can see here, just randomly by varying the network in such a way that we can only have one origin and one origin destination pair, and we can see all of this here, and all of these could have some characteristics that you know would result in variations in the congestion levels, which will be assessed by the traffic assignment or user equilibrium code in the model. Now, in the network that I showed now, we just looked at the correlations in the properties of the network. These are global measures, and we want to see which properties are more important here. And so by looking at the correlations, which I'm not really showing here, I selected these three measures to be representative of the network. And so when we select that, so for those 80 networks, we have those three global measures. And then we had variations of the remaining variables, which I'm going to show. These are the variables, other variables in the model. Apart from the network configuration, we have the iteration rate, we have the user cost rate, traffic factor, discount factor, and we have the range of values that they can assume. So we vary all of these, and we have them to the network properties table, so that we can have several combinations of these variables together, which are going to be the scenario, which are going to be considered as decision scenarios for which we want to use the models. And so when I did this, I had about So the next thing is, after adding the variations, the next thing is to characterize the data sets, like I explained in the chart, and label them, so that, because currently it's on label, so we want to label them the way I explained previously. And then we're going to train a classification model with that. So after doing all of this, this is what the data set looks like. The data set, which I said is not a real data set. So we have this these network properties, which are three, and this is just a section. I just copied this section out. We have about 10,000 scenarios now by and then we have the iteration rates, we have the discount factor, we have the agency, we have the user cost, and this, we see that there are changes here. These two rows may seem similar, but we see that the average asset condition for this is 1 and this is 2. And then we can see that the OD demand is 6,000 here and this is 2,000, even though this and this may seem similar. But the whole idea is to generate all possible combinations of this so that we can have a decision, a data set for the scenarios. And then we use a cluster analysis to label the data set as either, to characterize the data set as either a complex or a less complex, which I defined by group 1 or group 2 here. And then here, I label the data set by, in the previous slide, I said that currently one of the things that we did is to look at the total cost, for example, and see if the difference between them is at a certain percentage. If it's more than a certain percentage or is less than a certain percentage, then we should assign a black box model or a simple model. But this is just the case for now. When I finally do the real simulation, yeah, obviously this definition of the threshold may change later. But just to illustrate, this is what is being done to label the data set. And so and then the next thing is, after labeling the data sets, we remove the life cycle cost and this life cycle, the percentage difference, because the whole idea is, when we have these scenarios, we do not know the life cycle cost component, but we want to know, when you have these scenarios, we want to know what model is appropriate to use to determine this. So that's why, before developing the classification algorithm, I'm dropping these three variables so that we can just use these scenarios to determine the model choice to use, and then we can now use that model to determine the life cycle cost that we want to um, determine. Now, so this is example logistic regression. Yeah, this is the accuracy is 82% and F1 score is 0.9. But obviously, we see here, looking at the confusion matrix, that this does not make sense, because it doesn't seem to be classifying this zero class properly. But again, it's because this is a kind of randomly generated data, just to illustrate the process of what is being proposed here. So it is expected that with a real data set, this should not be the case. But for illustration purpose, that is why it is. And I said that possibly the reason why this is so is because the data set is unbalanced currently, and label 0 is being misclassified, and that's is not expected of hopefully when we have a real data set. And so when the model is developed, the next thing would be to define a new scenario. When you want to make a decision, you have a network you want to make a decision on, you have the discount factor for that year, you have the derivation rate for the segments, and then you've defined a scenario. Then you can use that in the model to predict, okay, this is we can use that in this model, this classification model, which I call the model of models, to predict what model to use. Then when you now know the model to use, because that scenario says that this is the best model to use, then that to an extent would give additional layer of fidelity to the user, because now the user who is initially skeptical of the outcomes of the model all the implementation process of the model, because the model is a black box, now understands that, okay, yeah, this may be a black box, but it is really worth it to use this model under this scenario. It is worth it to use the other model under this scenario. So that's the whole idea of this exploratory process for the models. And in conclusion, after looking at literature, and the experiments that we've done, we can say that, yeah, there's truly some skepticism in the adoption of decision support tools by the asset managers or engineers at the transportation agencies, because of the things I've said, and obviously because of the experiment that we have run as well. And and um uh, experiments so far have confirmed that. And I showed previously that a variance-based sensitivity analysis can potentially be used to understand this, complex behaviors between the parameters. And lastly, based on the illustration of the model of model framework, which I presented, I believe that is realizable. And hopefully when we have a real data set to illustrate that, we can potentially have a template for which we can use to explore our models better. And that is all I have. And this project is supported by the grant from CMTs. And I thank you very much for listening, and I can take your questions now.
So I have a question. Um, so first of all, very good presentation. Thank you very much. It is a very interesting research about how we can choose a model to perform our analysis. So I just want to ask a clarification question. So in my understanding that your choice here is like which model to choose. So I wonder, is it like a binary choice of the black box or a simple model, or you have like multiple models for black box, multiple models for like simple?
All right, thank you. So the illustration here is a binary classification, but the whole idea is not gonna be binary, because we, as researchers, we continue to develop models. A lot of these models
Yes.
are there, but there's no way to really assess the cost and the benefit of these models. The cost in this case would be like what computational resources is going to be used. If as a decision maker, you need to run a model for 7 days to run a model to make a decision now.
Mhm.
And obviously, maybe the benefit at the end of the day, the life cycle cost that you're going to get is going to be in the range of another model that's probably would just require like 2 days or 1 day. Then this kind of model can just tell you ahead, okay, see, I've run this. This is a set scenario. I've explored different scenarios that could ever be envisaged. Now, this new scenario that you have, I think it's better to just use a simple model. You'll be okay doing that. And in the industry, when decisions are made, we all saw the case of the bridge that collapsed recently. A lot of decisions, that bridge now is taking a link away from the network. Decisions have to be made instantaneously, immediately. You can't wait for a model that's gonna take like a week to make a decision, right? At least at
Yes.
that instance, you need to make a decision instantly on, okay, for decision maker to at least progress with some decisions at that point. So in summary, the idea would be, as an agency, you have multiple choices to make a decision from, you have multiple models to use to make a decision. So which one of them would be the most to use here? So because also people may just be using simple model. Usually there's this tendency for engineers to just want to stick to the simple one, which they understand, which is clear to them.
Mhm.
But when you can show to them that, okay, all of these models, I think it may be beneficial to use the complex models under certain scenarios. So yeah, so that would be the idea, to explore all possible models, all available
Yeah,
models, rather. Yeah.
yeah, that makes sense. Thank you very much.
Thank you.
Thank you so much for the presentation and for answering the question. We are going to move on to our second presentation to keep to our schedule. For that, Dottie Bhargavi, are you able to share your screen?
Yes.
I'm going to do a quick introduction. So our second speaker today is Dottie Bhargavi. They graduated with a bachelor's degree in civil engineering from NIT Trichy. She is currently pursuing a master's degree in transportation engineering at IIT Kanpur under the guidance of Dr. Maduri, with a focus on pavement engineering and predictive modeling. Current research includes comparison of survival analysis and logistic regression models for pavement crack initiation prediction. So please take it away.
Oh, thank you for the introduction. Is my screen visible?
Yes, it is. It's on the...
But it's on a different slide, yeah. You might want to start at slide 1.
Good morning. I'm Bhargavi. I'm doing masters in IIT Kanpur in the topic comparison of survival analysis and logistic regression methods for pavement crack initiation. And my supervisor is Dr. Maduri. And the motivation is to study the different modeling techniques for time to event data. And time to event data is basically where we study about the time until the occurrence of a particular event. And that event can be anything. It can be death of an individual, or it can be relapse of disease from the treatment, or it can be a failure time of a structure. Or in this, I'm usually focused on time to crack initiation. In a transportation setting, the most common areas where it is used is time until the failure of a pavement or time to crack initiation. In some cases, it is also used to model the waiting time and also the clearance time in case of traffic incident duration. And by studying this time to event, we can understand the disease progression and also how different treatment methods will be effective in case of health sciences. And in case of infrastructure management, it helps in preventive maintenance and rehabilitation activities. And the different, like as I suggested, the time to event data is modeled using the survival analysis. So why survival analysis? Usually the time to event data is incomplete, as in some of the observations don't experience the event by the end of the study period, due to which we don't have complete data about those observations. So this phenomena is called censoring. This is quite common in case of this kinds of data. As you can see, if we consider there are 6 observations in the study, the first and the third observations have not cracked by the end of the study. All we know about those observations is they have their failure time greater than the particular limit, but we don't know what is the exact time. So if we neglect this phenomenon and model, it might lead to unbiased estimate about the failure time. And there can be different types of censoring. Right censoring is when we know the failure time is greater than this time, but we don't know what is exact time. Left censoring is we know the upper bound of the failure time, but we have no idea about the lower bound. Interval censoring is we know the interval in which the failure of an event happened, but we don't know the exact time when the crack has appeared. This study is about the crack initiation. So how censoring exists in inspection data. Usually the pavement inspections are carried at fixed intervals of time. So in this example, if we consider T1, T2, T3, and so on are the inspection times. And let's say at the start of the study period, there are N1 sections. Those sections are considered to be at risk at the start of the study. And by the time of the next inspection time, T2, let's say D1 sections has cracked. So at T2, the number of sections at risk will be N1 minus D1. So this is the usual inspection data. So if by the end of the T6, if some of the sections have not cracked, then those will be considered as censored. The notation RTI indicates the risk set at TI, which is the set of sections which have not failed or censored by that time. So if we apply traditional linear regression to this, it leads to underestimation of the survival time due to the presence of the censoring. Before moving to the analysis, I'll just explain the basic notations. For each section, there is T, which is the true failure time, and C, which is the censor time if the observation is censored, and the observed time, which is the minimum of failure time or censor time. And for each section, there is also a status indicator indicating whether the section has cracked or not. It is 1 if the section has cracked, and if it is 0 if it has not cracked. So the survival data is of the form T1, which is the observed time, and X1, which is the properties of the sections, and delta 1 indicating the status. So from survival analysis, we basically interested in estimating the survival function. Survival function indicates the probability that a section has survival time greater than that time t. So if t is the random variable, then S of t is defined as probability t greater than t. That is equals to 1 minus the cumulative density function. Along with the survival function, there is another way of modeling this data, which is by using the hazard. Hazard is the instantaneous risk of a section, given the section has survived till that time. So H of t is the instantaneous risk conditional on survival till the time t. F of t, S of t, and H of t are related. So if you model one of the parameters, the other two can be estimated. The different types of survival data analytics techniques. The most common is non-parametric. In case of non-parametric, we don't assume any distributional form for the survival curve based on the survival. In non-parametric, we don't assume any parametric form for the survival curve. So the parameter for non-parametric models, the estimation of the survival function is usually obtained by KM estimate, Kaplan-Meier estimate, and that is given by probability t greater than ti conditional on the survival till before that time is equals to the number of sections which, that have the survival time or censor time greater than ti given divided by the number of sections at risk at ti. So it is basically the number of elements in the risk set at ti minus the number of sections failed at that time divided by the total number of sections at that time, a total number of sections at risk at that time. Since it is a conditional probability, it can be iterated to obtain the survival probability at time ti. The next type of models is parametric models. The parametric models assume a distributional form for the survival time, and the distributional parameters can be modeled, can be varied to model the heterogeneity in the survival time among different sections. The most commonly used parametric models are exponential, Weibull, logistic, log logistic, gamma, etc. But if the data does not follow the assumed distribution, then it leads to biased estimate of the survival time. So the third kind of model is semi-parametric, which is a hybrid of parametric and non-parametric. The most common semi-parametric model is Cox model. The Cox model is given by, usually Cox is modeled using the hazard. The hazard at time t is equals to a baseline hazard h naught of t into a parametric component, which is individual specific. H naught of t is the non-parametric baseline hazard, which does not have any distribution. And this e to the power of x beta is the relative risk of individual, and this depends on the regression parameters. So it has both parametric and non-parametric components. This estimation of the Cox model. Let's say T1, T2, T3 are the observed times of n individuals. So the likelihood function is f of t if it has cracked, and into S of t survival function if it has not cracked. In terms of hazard, it can be written as follows. Since the baseline hazard distribution is unknown, to estimate the parameters, there is an idea. Cox came up with the idea of partial likelihood. Partial likelihood can be explained as follows. Consider there are 5 sections in the study, and 3 of them has failed, and T1, T2, T3 are the unique failure times. Since 3 of them has failed and the rest 2 has not failed, those are considered to be censored. So for this, the partial likelihood is formulated as follows. At T1, since all of them has not failed, so the number of element in the risk set is 5. So the partial likelihood is probability that section 1 will fail given the 5 sections at risk. So it is written as hazard of section 1 by sum of the hazard of all the 5 sections. Similarly, at T2, assuming section 2 has failed, since section 1 has already failed, here the risk set has only 4 observations. So the partial likelihood is hazard of section 2 divided by the hazard of 4 sections. Similarly, at T3, this is the hazard. So assuming the failure times are independent, the partial likelihood is product of all these individual probabilities. Now, at a particular time period, the partial likelihood is basically predicting which of the section will fail given all the observations in the risk set. So this is equal to a classification algorithm at a particular time t. So the partial likelihood is basically equals to series of optimizing series of classification algorithms. So instead of doing multiple classification algorithms, there is an idea called stacking, where we stack all the risk sets and perform a classification algorithm. So since there is a binary indicator indicating whether the observation has cracked or not at that time, so this can be treated as a classification algorithm at a particular time. So instead of, as I said, instead of doing multiple classification algorithms, we can reshape the data set to apply the classification algorithm on the whole data set. So survival data is reshaped by stacking all the risk set, and we add a dummy variable indicating whether the observation is present in that risk set to account for the time component in classification. So this is the idea of the stacking. Let's say these are the observations in the study. X is the covariate matrix of the observations, and Y has the survival times and a binary variable indicating whether it has cracked or not. So at T1, since all of them has survival or sensor times greater than T1, all of them will be in the risk set. So risk set at T1 contains all the 7 observations. We add a dummy variable indicating that these observations are present in the risk set 1. Similarly, at next failure time, which is T3, since the first observation has the survival time less than T3, they won't be present in the risk set. So in the risk set at T3, these 5 observations will be present, and we have a dummy variable column indicating that these 5 observations are present in the risk set. And similarly, at the next failure time, these 2 observations will be in the risk set, and we stack all these risk sets to apply a classification algorithm. So this is overview of the difference between Cox and survival stacking. In Cox, the data is of the form xi, ti, where ti is the survival time or sensor time, and delta is the indicator whether the section is cracked or not. In survival stacking, xi, we have the covariate vector xi, and rtk indicating whether the observation is present in the risk set at tk, and delta is the indicator whether the section has cracked at that time or not. And in Cox model, time is explicitly modeled by h naught of t, whereas in survival stacking, the time is modeled by the dummy variable coefficient, which is beta rtk. The estimation of Cox model is using the MLE of the partial likelihood. In survival stacking, we estimate the coefficients by MLE of full likelihood. In Cox, it assumes that there are no tide failures, whereas survival stacking explicitly can handle the tide failures. So to test these two are simulated data, where the survival times are simulated from an exponential distribution. This is the distribution function of exponential. From this, the hazard is lambda, and this lambda is varied among different observations as function of 3 covariates, x1, x2, x3. and these are the population parameters of the beta, and x1, x2, x3 are distributed, are simulated from different distributions, uniform, gamma, and uniform. And to incorporate censoring, we set a limit of 25. Observations whose simulated time is greater than 25 are considered to be censored. These are the summary stats of the data. So when Cox is applied on the continuous data and logistic regression is applied on the stacked data set, the coefficients obtained from both Cox and logistic are quite close to each other. These are the coefficients. As we can see, although the coefficients in both cases are little off from the population parameters, in both the cases, the population parameter is present in the 95% confidence interval. So why the coefficients are similar? When we compare the likelihood, when we wrote the likelihoods of both Cox and logistic regression, under certain assumptions, both the likelihoods converge. So which is why the coefficients in Cox and logistic are close to each other. So in model evaluation, usually survival models are evaluated using C index, which is concordance index, and Brier score. C index is the number of pairs of observations whose survival probabilities are in true order compared to the true survival time. So it is basically the probability that the hazard of individual I is greater than hazard of individual J, given that the survival time of J is greater than I. Similarly, along with the ordering, to evaluate for the predicted values, Brier score is used. Brier score is the squared error between the status of the individual at time t minus the predicted survival probability. These metrics are corrected for the censoring to account for the loss of information due to censoring. So when the Brier score is calculated in case of Cox and logistics, since the coefficients are similar in both cases, we expect the performance also to be similar. And this is the Brier score in case of survival data and also in case of logistic. As you can see, both of them overlap with each other. The similar thing is also expected in case of C index, and that is what we are seeing in the data also. The C index of both Cox and logistic is overlapping with each other. Since C index is the number of pairs which are predicted in the correct order, the higher the better. Whereas Brier is the error between the predicted probabilities and the actual status, so lower the better. Similarly, this is applied on the empirical dataset, which is the Washington DOT dataset. In case of Washington DOT dataset also, the Brier and AUC are overlapping for both Cox and logistic. Now the idea is, since the performance is similar, if both models are specified as linear models, so if we made one model worse, we should expect there should be a drop in the performance. So we explicitly included some nonlinear interactions in the lambda. In Cox, these nonlinear interactions is ignored and it is incorporated in the logistic regression. So from the results, for logistic, the coefficients obtained from the logistic regression and the population parameters are quite similar, and the population parameter is present in the 95% confidence interval, whereas in case of Cox, the coefficients are off from the population parameters, and also for X1, the coefficient is not present in the 95% confidence interval. For X2, the confidence intervals are wider compared to the logistic regression. Similarly, when we compare the model performance, for logistic, the Brier is better than Cox. Similarly, for logistic, the C index is also better than the Cox. So the idea is, since logistic regression and Cox are equivalent if there are non-linear interactions among the covariates, So if there is a classification algorithm which can capture the nonlinear interactions, then it improves the prediction of the survival probabilities. So this way, using survival stacking, we can use the prediction power of existing machine learning algorithm to improve the prediction of the survival probabilities. This is the future work. In Cox also, there are in Cox survival models, there are machine learning algorithms such as random survival forest and gradient boosting methods to incorporate ride sensoring. So the future work is to explore feature engineering in both survival analysis and classification and compare the performance in both settings. And also there are another binary classification model where instead of stacking the dataset, they use the time as a covariate and model it as a classification model. So the future work is to compare these models with that alternative classification model. Thank you. Thank you. Questions?
Thank you so much for the presentation. Please feel free to speak out any questions or write them in the chat and we can communicate them.
Yeah. Also, go ahead.
Hi. Some interesting work, so fun. So as usual, there's a lot of detail in here. And one of the challenges, it's kind of like Babatunde's, is trying to communicate it to organizations to encourage them to use it where they traditionally use more simpler models. Have you given any thought to how do you get organizations to use these things?
One of the questions for you, yeah.
Well, once I make the comparison and find that there is no significant improve in the performance for this complexity, then one might also can use the simpler models. Or if there is significant improvement in the performance, then it is worth to use the complex model rather than simpler model.
So I think there's some parallel things between the two presentations, even though one would not have thought of that at the beginning. So that was just something that struck me.
That is true.
Doing
Yeah.
something similar. Yeah. Doing something similar.
All right. We'll do a last call for questions. Anyone?
I mean, one thing, just I mean, since Baba, a couple of, I mean, one comment with, yeah. So I guess on the note that Sue mentioned that they're kind of similar. We're talking about complex models and simpler models. So I mean, I guess one thing which is probably important, which goes for both of this, is if the baselines and under which we're comparing these two models, if the are similar, then it kind of makes sense to compare them. But if the worlds under which they're operating are very different, then the comparisons may also yield results which may not make sense. So one thing I was trying to go back and forth with Babatunde on the chat was, for instance, if the the constraints of the real world are there's an oracle with certain set of constraints, and then you're trying to simplify them by either ignoring them or keeping them, then the comparisons across the models may still be relevant if the solutions are feasible for both models and you're able to apply them interchangeably, and then recognizing whether the simpler model is a subset of the more complex model or is nested under the more complex model, or whether they're completely non-nested models speaking to where the reality is somewhere else, and then these two are just approximations of the true model, right? So for instance, like we know in the modeling setup, we don't really know what the data generation process is. So oftentimes then the search is for finding what that Oracle data generation process is. But I thought I'll just add my 2 cents on the comparisons of complex and simple, since we had some time.
Yeah, thank you very much for that. Yeah, I've noted those comments. Yeah, thank you.
And thank you for showing up at so early in the morning.
Thank you all.
It's not so early
It's
for me,
always
actually.
good.
I've said that with Professor McNeil. I think
Yeah.
she's earlier than I am. So,
It's all good. Yeah. Nice presentations, everyone.
Thank you
thank
all.
you.
And one thing I meant to say at the beginning and didn't is that Professor Durango-Cohen apologizes for not being here. He has his own presentation that got scheduled for during the day today while this was occurring. So Pablo was not here. He wanted me to send that message.
Sounds good.
Thank you all for coming.
All right.
And
Thanks, everyone.
hope to see you in the fall for the next VISIM sessions.
Thanks
Right.
again
Bye.
for organizing another round of VISIM.
Absolutely.
All right.
Thank you. Thank you all.
Thank you.
All right.